In this video, I'm going to show you a double integration trick. So let's say you're trying to integrate this, and the trick is that you can rewrite this thing here as this block here. Because if I were to give you this block, you would integrate this, that would then give you inverse 10. So that would then give you inverse 10 of x. From x to pi x, from x to pi x, and then you would put this into here. That would be inverse 10 pi x, and then you would put this into here, inverse 10 x. This thing here is exactly the same as this. So the trick is to rewrite this thing as an integral, and then later on we can switch these two around so that we can easily integrate this, because we can treat this as a constant. So the aim is to switch these around so that later on when you come to integrate this with respect to x, it would be easy, because when you integrate this, it would just be 1 over, because you treat that thing as a constant. So the trick is to rewrite this thing here as this block and then switch these two around. Going back to here, yes, you can use single variable calculus to solve this. You could just integrate this, but this is just a double integration trick, so that one day hopefully it would make your life easier. So it's just a trick that's available to use, for you to use if you want to in the future. So hang on, so let's start again here. We're currently here. Rewrite this whole thing as this thing here. Now switch these two around, because we want to integrate it with respect to x first. But in order for us to do that, we need to understand the region, because we've got to decide our limits of integration. So we've got to decide on these things here, but we need to understand the region in which we are integrating over. So let's try and integrate this. Well, let's try and understand the region in which we're integrating over. So you're moving parallel to the y-axis. So you're moving along parallel to the y-axis like this, from this line to this line. So we have no idea what's going on. So let's just blindly sketch this line, y equals x. It will look like this, y equals x. And then blindly draw this line, y equals pi x, which looks something like this, y equals pi x. So you're moving parallel to the y-axis. You're moving parallel to the y-axis like this. But you have to start at the line and end at the other line. You have to start at the line, end at the other line. Start at this line, end at the other line. Start at this line, end at the other line. Start at this line, end at this other line here. And then you're scanning all the way through from 0 to 2. So you're scanning from 0 to, let's say 2 is here, 2 is here. So you can see that this is our region. So we are interested in this region here. So this whole region here is this region here. Okay, so let me just enlarge this diagram. So it looks like this. So we are interested in this region here. So currently we are doing it like this. We are integrating from the first line to the second line, from the first line to the second line. But then if we want to work in terms of dx, we need to integrate it like this. We need to move like this. We need to move like this. We need to move like this to cover our region. If we want to work in terms of dx, we have to move like this. But then this is one region here. And then you got to break it up into two regions, because you got to start from here to 2, from here to 2. Down here was from here to the diagonal line, from here to the diagonal line, from here to the diagonal line. Up here is from here to the number 2, here to the number 2, here to the number 2. Meaning we've got to break it up into two different integrals. If we want to work in terms of dx. Up here it was in terms of dy. Dy it was quite neat. It was like this. Dy was quite neat. It was like this. It covers up the whole thing. But then if we want to work in terms of dx, we've got to break it up into two integrals. So one region which is this one here, and this region here is this integral here, and hang on, and here if you're moving along in the x direction, so here you start at the you start at this line here, which is this, and then you finish at this line. You start at this line, you finish at this line. You start at this line, you finish at this line. You start at this line, you finish at this line, and you're scanning from y equals 0 to y equals 2, from y equals 0 to y equals 2. So your first region is this. That's your first region. And then your second region, well, you start at the diagonal line, and then you hit the number 2. You hit the number 2. You hit the number 2. And then you start at the diagonal line, which is here, and then you finish at the number 2. You start at the diagonal line, and then you finish at the number 2. And you're scanning all the way through from 2 to 2 pi. You're scanning all the way through from 2 to 2 pi. Well, this whole region here can be set up by using these two integrals. Okay, so we are currently here at the moment. So now if you integrate this, it will give you, well, if you integrate it with respect to x, if you integrate it with respect to x, you can treat this whole thing here as a constant and then stick an x in there. The x gets multiplied to the top, giving you this. So when you integrate this, it will give you this, from here to here, from here to here. And then if you integrate this with respect to x, it will give you this, from here to here, from here to here. So that will then take us to here. And then now, hang on, and now we've got to put this into the x. That will then give us this. Take away, put this into here. That will then give you this. And then put this into here. That will then give us this thing here. And then put this into here. That will then give us this thing here. Glancing at this you know is easy to integrate because this is near enough the exact derivative of this. So you know it's easy to integrate. This is easy to integrate because this thing here is a constant. Why? Well, this is easy to integrate. From Calculus 102, we've done this already. If you integrate this, it will give you. Hang on. If you integrate this, it will then give you this thing here. If you integrate this thing here, it will give you this thing here. This is also easy to integrate because this is near enough the exact derivative of this. So if you integrate this, it will give you this thing here. You know that if you have this, it's quite easy to integrate, but we haven't got y there. But it turns out that if you integrate this, it's actually the inverse 10. Well, we've done all this integration thing before. So if you integrate each individual component, it will give you this whole thing here. And then that will then take us to here. Hang on, let me just move this across. Hang on. Okay, so we are currently at this stage here. So now now put the 2 into here, so that this whole thing here, the number 5 is never negative, so we can ignore the absolute sign. We don't need absolute of the number positive 5. Well, anyway, put this into here. That will then give you this. Put this into here. That will then give you this. And then you take away. Hang on, let me think. And then you take away. Put 0 into here, which will then give you natural log of 1. Natural log of 1 is 0. It would be 0. Put this into here. You're going to get natural log of 1. Natural log of 1 is 0. It will give you 0. So now, so this whole thing here will give you these two. And then now put this into here. That will then give you this thing here. And then put this into here. That will then give you this thing here. And then you take away, put the 2 into here. That will then give you this. And then this into here. Take away a negative here will give you a positive. It will give you this thing here. So now we are currently here. So hang on. So if you tidy this up, I think this thing here would cancel out with this thing here. So overall it would be this, which is approximately this. Okay.